So again, there are several different regions wherever we're doing these titrations. If we're talking about a strong acid, strong base, then the resulting conjugate acid base is going to be a salt. And so because it's strong acid, strong base, the conjugate acid base doesn't have any basic or acidic properties. Okay? And so if you neutralize, you get to the equivalence point with a strong acid and strong base, your pH is always going to be pH 7, right? The pH of the solution. Now, again, that is only for a strong acid, strong base titration. So what happens after equivalence points? Well, you just have excess base, don't you? Okay, so whatever you're titrating with, you're going to have excess of that. And so, for example, in this case, after equivalence point, we're going to have an excess of 0.5 milliliters of that HBr in this case. And so we just have to calculate the H plus from the dilution of that HBr, don't we? And so again, here's our initial concentration of the HBr. This right here is our dilution formula. We've added 50 milliliters. This is a total volume of 50 plus 10.5 milliliters, which came from that other volume that we've added 10.5 right here. Okay. And notice it's just a dilution, isn't it? Okay. And so we get our concentration of our excess H plus. We then take the negative log of that concentration, and that gives us right here our pH. Now, note that there is a little bit of wiggle room around an equivalence point, okay? And those equivalence point wiggle room is going to be where you have such a small concentration here that you're near the Kw ionization of water, right? So if you had like a 10 to the negative 7, 10 to the negative 6 sort of concentrations here, you'd have to account for the Kw, the autoionization of water, right? Okay. Like all the information we talked about in the previous chapters didn't go out that window. It still exists. We just get to ignore the activities for the most part in most of these equations. Now, for the regions of a weak acid, strong base titration curve, number 1 is going to be before the titration begins. You've not added any base. The solution is going to be your weak acid. Now, when you're talking about a weak acid, remember you're going to have an equilibrium, right? Most of it's going to be in the form that is not ionized, that is not dissociated in solution. Okay? And so that is going to be the weak acid equilibrium. Before the VE, there's going to be a mix of the unreacted weak acid and the A minus, that's the titrant. Notice that you're establishing a buffer, aren't you? And so for a weak acid being titrated, this first part, after you've added some base, and then up to the VE, is going to be referred to as the buffer region. Okay? And you can just directly use Henderson-Hasselbalch's equation during that region, because it's just going to be a buffer. You've made a buffer. You've neutralized a part of the weak acid, part of it, you have a mixture of a weak acid and its conjugate base. Okay. So at VE, you're going to convert all the HA to A minus. Note, it should be quotations all. It's probably not actually going to be all. It's going to be somewhere nearby. Okay. Now, the pH is going to be determined from your weak base equilibrium. At that point, what you have in solution is the weak base, don't you? Okay. And so what you've actually done is you've converted it to a weak base solution at the VE. Now, note that because this is a weak base, are you ever actually going to be, like, is this going to be pH 7? So in a strong acid, strong base solution, we had a salt, right? Which was not base, is it? Okay. So this is going to be a weak base. So its pH is going to be above 7. Has to be. Because you've made a bunch of weak base, haven't you? That's what you made. And so pH is going to be above 7. It's going to be a weak base. It's going to be just the weak base equilibrium at this VE, right? The equivalence point. And that's all you're looking at in terms of what the pH is, what the concentrations are. Notice because this is a weak base, there's actually a lot of the A- that will not be A-. Okay? You've just happened to titrate away all the active acid. Okay? Now, your VE, this is going to be the excess unreacted NaOH. It's going to be added to a solution of the A-. The pH is going to be determined by your excess strong base in that case. You're going to overwhelm that weak base, and you're going to be a strong base solution. That means you're just straight up doing the dilution of the strong base. Okay? That's the only really meaningful part of this. Now, if we go ahead and consider this titration with 50 milliliters of MES, that's 0.02 molarity, with 0.1 molarity of NaOH, then again, the first step is going to be where you have that weak acid. And so this right here is your weak acid. Do I have to write these entire things out, by the way, to do my equilibriums? No, all the weak acids are the same, aren't they? The only thing that matters about them is their Ka and how many protons they have. So every time I do this, I can just put HA. I don't have to actually write out what it is. Okay? Doesn't matter. If I have my pKa, then I don't really care what it is. I just care it's going to do an acid-base reaction, don't I? And so, I have my weak acid. It's reacting with my OH-, creating my conjugate base right here. And so that's going to be the reaction as you add this NaOH, right? That's the reaction we have to deal with. So the next thing you're going to do is you're going to calculate the volume to reach the equivalence point, which is your VE again. And so if you have this reaction, it's going to be the reverse of the Kb reaction for a weak base. So if you have the Kb, it'd be 1 over Kb for the K, just the K, which is the equilibrium constant. If you're trying to get to Ka, then it's going to be Kw over the Ka to get the base, Kw over Kb to get the acid, right? Okay, so if we're trying to figure out what this base here is going to be, what the pH for this base is going to be, well, at the equivalence point, what is the reaction? Well, we have all this base, right? That's the predominant equilibrium at the equivalence point. So we need to take Kw, divide it by the Ka, and this is going to give us our Kb to do this. Now, our equilibrium K is pretty large here. And so this does go to completion after the addition of the OH-. And so our millimoles of base here would be this number. Again, that's the volume of the base times 0.1. The volume of the base in this case is the VE, because we're trying to figure out our equilibrium concentration, right? Our equilibrium volume. This right here is going to be the millimoles of the HA. And again, the reason it's millimoles is because we're doing milliliters here rather than liters. You can freely do everything in millimoles. It's not a problem. In which case, everything's in milliliters instead of liters. Okay. And so we multiply the HA volume times the concentration, right? That gives us millimoles. We're going to take this number and divide it over, and that's going to give us the 10 milliliters. And so that's going to be our VE, our equivalence point. Okay. Now the next thing we have to deal with is let's go ahead and look at the acid reaction so we can figure out the pH. So before this base is added, your solution would be 0.02 molarity of HA. That has a pK of 6.27. And so if we go ahead and plug this into our normal expression we've been using to figure out the concentration of H plus / A minus, right, in all these problems. So that's x squared over the formal concentration minus x, right? what we'd do here is we'd have the Ka here. That's 10 to the pKa, right? 10 to the negative pKa. Right there. This right here is the 0.202 molarity of that weak acid there. And then minus X on the bottom. Okay, we go ahead and solve for that. In this case, if you ignored this minus X here, that'd be fine. Okay. But if you want to do the quadratic, you can. So we solve for that. We're going to get 1.03 times 10 to the negative 4 molarity. That's that X value. Notice that would be the concentration of the A minus. That would be the concentration of the H plus. When we just have the weak acid, we haven't done any titrating yet. And so we take the negative log of that, and we're going to get pH of 3.99. Okay. And again, that's region 1. We have not added any of the base yet. This would just be the weak acid equilibrium, right? Because we haven't added any base yet. Okay, let's look at the next region, region 2. This is where we've added some base. Some amount of base has been added, but we have not gotten to the equivalence point yet. Okay? So again, whenever we're doing it up to the equivalence point, but we have not reached the equivalence point yet, we can treat this as a buffer, because we're going to use up some of that acid to make its conjugate base. Okay? And so, yeah, it's not a super effective buffer, probably. This is a very low concentration buffer, right? But it is a buffer. Okay. Now, when we've added 3 milliliters of the OH minus here, remember that that's going to be 3/10 of the way to the equivalence point. Okay? These are easiest done if you've already calculated out your equivalence point. Right? So whenever you do these problems, it actually behooves you to go ahead and calculate out the equivalence point first. Right? The reason for that is then you can just do everything and how far you are to the equivalence point. At the equivalence point, you have used up one of the forms, right? Making sense so far? Okay. And so we put in our pKa, which was provided to us in that way. So that's really easy. And then it's plus log of base over acid. And so in this case right here, we're 3/10 of the way to the fully basic form, aren't we? So our amount of base is 3/10. On the bottom here, we're 7/10 of the way away from the fully basic form. So 7/10 is still the acid. Okay. And that's why life becomes really easy if you go ahead and calculate the V. Again, this would be the number of milliliters you are to the VE. Everybody see it okay? This calculation happened to be 10 on the bottom, which makes it look nice. But if this was 23.25, it would be 23.25 down here. Okay? If this was 1.9972, it's 1.9972 milliliters up here. Okay? Like, the numbers don't have to be nice looking. Feel free to use some weird decimal place numbers, whatever. Doesn't matter, okay? Doesn't affect the math. It's just how far along are you to the equivalence point. Okay? This is just a faster way to do it. If this ends up confusing you, if you get on your exam, you go, what the hell was that again? If for some reason you struggle to calculate your equivalence point for some reason, your VE, then again, you can still just calculate out millimoles here and put the millimoles in each place. Okay? There's nothing that stops you from doing that. Just oftentimes you'll find out that you'll end up calculating out the VE and you need the VE for something. And so you'll already have VEs. If you already have VEs, then you can just directly put in your number of milliliters and then subtract your number of milliliters from the VE. Okay? And so your math becomes much faster. Now, again, this is region 2. This place in region 2 is a little bit special And biochemistry really loves this place because it's special. And again, this is 1/2 VE, right? So if you go to 1/2 VE, then pH equals pKa. Yeah. And again, this is still true. If this was 5 out of 10, 5 out of 10, they'd cancel out. You'd be left with 1 here, right? And you'd still end up being pH equals pKa. Okay? It's still true. It's still the same thing. Now, this right here is region 3. This is at the equivalence point. So when you're at the equivalence point, don't forget we have converted it all to the basic form, right? Theoretically. So your base is going to be your equilibrium, right? So your base is going to be doing the reaction with the water to form its natural equilibrium, right? And so all we need to do here is we need to find out the Kb and just do this equilibrium as if we started with the base. Okay? So all of your concentration that was listed up here, that formal concentration, that's going to be your concentration for formal concentration with the base. Okay? Right. Now remember that this concentration right here, the millimoles, is the same, right? What happened to your volume, though? Is there any difference in volume once we're at VE? If we started with 50 milliliters, then added 10 milliliters, is that volume still the same thing? No. So you do have to take into account the dilution that happens here, okay? So be aware that yes, that previous acid formal concentration, that millimoles from that hasn't changed. The amount of your acid is same as the amount of your base, okay? But your volume has changed, okay? Okay, so once we have the Kb, once we've done the dilution, we can go ahead and go into the problem. I will give you a formula that will do all of this for you if you want to be able to do this quickly, which is this formula right here. So this is actually that dilution factor right here. So again, Kb equals Kw divided by Ka, right? By the way, if you have pKa's, is there a faster way to get these numbers? I could have taken 14 minus my pKa, right? Then gotten my pKb. And then 10 to the negative pKb would have been the same thing. Okay. So again, we have that formal concentration. We have a modified formal concentration now, don't we? Is everybody aware of what the prime here stands for? It means a modified value. That's all it ever meant. If you see it in biology, specifically, it'll be physiological condition, because that's the important modified conditions they always care about. Okay? But if you see a double prime, that means a further modification of that. If you see a triple prime, a further modification from that. Okay? Every time you see primes, it's just a modification of it. Or it would be the other state. By the way, if the conformers, if you ever see a conformer and there's two options, they're both symmetric. The other option would be like a gauche prime versus the gauche. Okay? Okay. Now again, formal concentration, just the formal concentration of the acid, times the 50 you added, divided by the 50 plus the 10, which is the excess base you added. That's the equivalence point, right? All right. And so we again plug these numbers in to our x squared. This time it's going to be a new formal concentration, which is the F prime. And then that's minus x again on the bottom. This is going to equal Kb. Notice your Kb value is very small here. And so it's a very safe assumption to make that you can just ignore this minus x value. Does everybody understand when I say you can ignore that minus x value down there? Okay. You can just, you still have to solve for the x squared, right? Nobody's confused about that at all? Okay. Yeah, sometimes I get asked that. People get confused about that one. Again, it's the plus and minus areas that you can ignore. Okay. Now, we go ahead and solve for x. We get 1.76 times 10 to the negative 5. And we take the negative log of that. And notice we get a pH that's above 7, don't we? We get a pH of 9.25. So note at VE, whenever you're titrating a weak acid, by definition, that has to be a weak base at that equilibrium point, doesn't it? You're doing equilibrium for a weak base. And so your pH should always be above 7. It's basic. Okay. This is why, for example, when we did those titrations, you don't end at pH 7. Because you were taking a weak acid and making a weak base from it, right? Okay. Now, let's go ahead and look at region 4. This is going to be past the equivalence point. So, after we've hit the equivalence point, every single drop of that NaOH we've added is going to be excess OH minus, right? And so after 10.10 milliliters of NaOH, we're going to have an excess of 0.10 milliliters of OH minus. And so here's our initial concentration of OH minus right there from this right up here. And again, we take the excess here, which is the 0.1. We divide it by 50 milliliters plus the 10.10, which is the amount we added here, right? And then that's going to give us the concentration of OH minus. Now note that you do have the concentration of OH minus you're getting here, so you have to take that and get the H plus concentration. So Kw divided by the OH minus concentration, then take the negative log of that. Okay? And so your pH 10.22. Now again, that number always needs to be higher than this number here, okay? If the number is lower for some reason, then you have done something terribly wrong. Okay? All right. Anybody have any questions? Okay, so for that problem, this would actually be the numbers for everything. And see the different regions and how they respond to these numbers. Okay. So again, initial, that's just the equilibrium of your acid. Buffer. Notice the buffer region, you're going to have a very slow raise in pH. It's still going to go up, but it's just going to be very slow. Okay? And then you hit your equilibrium point, you get a big jump, right? Okay? And then the regions right after and before your equilibrium point are going to have big jumps, aren't they? Okay? And then you go over here in your region 4, what's going to happen is you're going to have big jumps at first, but eventually you're just adding OH minus to more OH minus, right? And so you get a tailing off, and it plateaus to whatever your concentration of your OH minus you're adding is. Okay? Okay. And that's what it looks like. So note, you have an inflection point. This is going to be where you have the minimum slope. And so your minimum slope is always going to be your inflection point. And that is your pH equals pKa. And so the inflection point, or your minimum slope, that's going to be 1/2 your VE, isn't it? Okay? And that's where you have your slowest change, isn't it? Because it's the buffer region. Up here, you're going to have the maximum slope. That's the other inflection point. And that's going to be your equivalence point. Okay? Every single titration always looks like this. Again, it may be several of these stacked together if you have something that's diprotic, triprotic, etc. But it always looks like this. Okay? It would just be more of these up here. Right. Anybody have any questions? Okay. Does everybody see that, realistically speaking, we haven't added anything to this? This is just the previous material. Now we're adding base to it and acid to it gradually. Okay? We're just doing it in steps. All right. Again, this is going to have your titration curve. This is going to depend on your acid dissociation constant of your HA. The concentration of reactants is also going to change your titration curve. So the inflection is near the VE is going to decrease as your HA becomes a weaker acid with a higher pKa. And the concentrations of your analyte and titrant decrease. So if we decrease the concentrations enough, we're again going to get a very flat titration curve. Okay? All right, so this right here is your pKa. So here we have a strong acid, and notice it looks like basically a sigmoidal curve, right? And then we start doing weak acids with pKa's of 2, 4, 6. And what do you notice about this? We get more and more buffer region, which then leads into our inflection point here, right? Your VE. Okay, equivalence point. If we get a weak enough acid, well, then it's going to have the base part so close to the inflection point that you get almost no curve. Okay? And so at like pKa 10, you see almost no curve at all. And your VE region has, I mean, it's still the maximum slope. You can still see maximum slope, right? But it's just really, really not an impressive slope, right? Very little change. That's this right here. Over here, we see the decrease in concentration. So if you have more concentration, what's going to happen is you're going to have these huge jumps. Can everybody see okay? And so you get a very, very, very distinct, huge increase in pH, right? As you decrease your concentration, what you're going to see is, again, your maximum pH is going to be suppressed here. Okay? And there's going to be a lot less difference in that maximum pH versus your initial pH. And so as you get to small enough amounts, you're going to have, again, a very, very minimal inflection point. It's going to be very shallow, and it's going to be very difficult to detect, if it is even possible to detect it, to be honest. Okay, so let's look at an auto-titrator precision for the titration of alkalinity in water. This is the concentration of the carbonate in the water. This is your alkalinity, which is a factor of your carbonate in your water here. And this is your relative standard deviations. And so this is one of the reasons that's so important, is when you're actually testing real-world samples, you don't necessarily get to choose their concentrations. You get to manipulate them a little bit, but you don't completely get to choose. And so if we have very low concentrations, what's going to happen to our percents or relative standard deviations? It go way up, right? Why is that? What's going to happen is you're not going to have much of an inflection point, right? So it's going to be very difficult. Like on this, where is the VE? Is it over here? Is it here? Is it here? Mm-hmm. You basically can't see it, right? Only reason it looks like there's a VE at all, really, is because you have the other titrations to reference. So, yeah. It becomes incredibly difficult to detect those equivalence points when you have very low concentrations. Okay? It also has the same trend of detection when you have these very, very high pKa's for an acid. Okay, now if we're looking at the titration of a weak base with a strong acid, it is literally just the opposite. So every single region's just the opposite. Remember, we're starting with a weak base, so that means our starting conditions is the equilibrium of weak base, right? And then the second region is, again, going to be a buffer region. But remember that, again, you're with the base, okay? So this formula is typically formatted in such a way that's acid dependent, okay? And again, this is the H+, right? So it's acid dependent. Okay. So remember, you're probably going to have to take, unless you already have a pK, you're probably going to have to go 14 minus the pKb, okay, to get this value. Don't forget your base, which is what you're going to start this with, is going to be on top, and then you need to put the acid form on the bottom, okay? So it's a bit different direction. So at the VE, what have you made? Well, you're titrating with an acid in this case, so you've made the conjugate acid, haven't you? And so at VE, it's just going to be the equilibrium of the conjugate acid, okay? And you just do the equilibrium of the conjugate acid. Again, it's still going to have that modified formal concentration because you still diluted it. Okay? So very, very similar. After the VE, don't forget, your pH is going to go down. So by the way, what would the VE be? Would it ever be pH 7 for this? At the equivalence point? No. And it has to be a weak acid, right? And so if you're titrating a weak base, you always have to be below pH 7. Okay? Because it's going to be a weak acid you make. Okay. And so after the VE, again, remember you're going to just be adding acid. This does actually mean that after the VE, this equation becomes super easy because you're just going the concentration, whatever your dilution of your strong acid is, that is your concentration of H plus, right? You don't have to go Kw divided by blah, blah, blah. No, you just plug that into negative log of that concentration. There you go. Okay. Okay, this is actually the example we did at the beginning here. And so this is one everybody got right. Great job. I love seeing that sea green. That's awesome. Okay, fantastic. Okay, and so this is actually the one where you calculate the VE, right? So if you're going to do a series, like an entire titration, well, then calculating the VE makes life really easy, doesn't it? Okay. That's why all the titrations we've done, like the first step in the packet is always calculate the VE. That makes everything else easier, as you've learned the hard way. Which, fair enough, right? That means the memory will be more memorable. Okay, you all get out in your careers, and you'd be like doing a titration. Wait a second, calculate V. Here, let's move on. No. Made this mistake before. Wait for it. I can see you. You'll probably have like flashbacks. No, Dr. Clausen! No, I need to wait for the V. Let me calculate the V. Okay, so again, this would be a calculation of V. And so we have this titration reaction right here, which would be your base plus your acid, gives you conjugate acid. We plug these numbers in that we were given on the previous slide. And again, that's a 1-to-1 ratio. And so what we get here is 25 times the 0.086364, then divide by the acid concentration, which is 0.1067. That gives us the VE of 19.60 milliliters. So the pH at that point, when we have the VA equals 4.63 milliliters. So first off, this is the next problem that I had you do on the deal. And this is the one that some people had a little bit of trouble with. Okay. I'm going to let you recalculate it here, and then you can re-answer if you'd like. Now, when the pH, what would be the pH when the VA equals 4.63? So what region are we in? Buffer region, exactly, before the equivalence point. Okay, so we know our VE is this, right? So the easiest way to do this problem is actually just take this number divided by that number, right? And then this minus that over that for your other concentration. Okay? Okay. So again, we have the base form is going to be on the top. So we take our pKa, that's 5.20. We take the 4.63 divided by the 19.6, and that's going to be 0.236. That's going to be the number on the bottom, which is the acid form. Because remember, we're titrating with the acid. And that's the amount of acid we made. Okay? So we go ahead and take that difference out of 1, because if they'd been the same number, it'd be 1, right? Okay. So 1 minus the 0.236, that's going to be 0.764. That's the remaining amount of base, isn't it? That we haven't used up yet. Okay. And so that goes on the top here with the base. See how we can just easily do the relative amounts? Saves us a lot of time, doesn't it? Okay. And so we plug those in, this divided by this, take the log of that, and what we end up getting is 5.71. That's going to be our pH. And that's the answer to the problem. Anybody have any questions there? Okay. Let's look at titrations of diprotic systems. So diprotic systems are just going to follow that same math we looked at before. They're just going to be different regions, right? Now, notice that these middle regions, we have to treat them as diprotic regions, okay? So they have two equilibrium that are affecting those regions, okay? Right. So again, here we have a base. We're going to titrate it with HCl, and we have two pKbs right here, okay? Notice again, we have a weak base. Then we're titrating with HCl right here. Everybody okay with that so far? Okay, fantastic. All right. So again, it's going to have that same sort of regions, right? We're going to have our pure base region, right? Then we're going to have a first buffer region. Then we're going to have an equivalence point, okay? And then we're going to have our second buffer region. And then we're going to have another equivalence point, right? And then we're going to have where we used up all of our diprotic, right? And so we're just adding more of the strong acid, okay? Okay. So the first VE1 is going to be 10 milliliters because that's how much millimoles it takes to go ahead and neutralize this sample once, right? Now, notice because this is just purely millimoles, right? It doesn't change for the second deprotonation, does it? That VE doesn't change. It's still going to be the same VE number because you still have the same number of millimoles, don't you? Okay. And so every time we look at these diprotic, triprotic systems, diprotic, you're going to second one is always going to be 2 times the VE1. It's just going to be 2 times that number, period. That's every time. If you had a triprotic, it would be what? The last one? 3 times. Yeah. So your first deprotonation is going to be complete when you're at VE1. Your second deprotonation is just 2 times VE1. Third deprotonation, 3 times VE1, right? And you just keep doing that. Okay, so again, there's 5 points on your titration curve that we have to focus on. There's the before the titration begins, so this is just going to be the base equilibrium in this case. Okay? And so just weak base equilibrium, that's it. And so we go x squared over 0.1 molarity, because it's 0.1 molarity right there for the base, minus x. This is going to be equal to the Ka here. Remember when we're looking at a, Kb here, notice when we use a pKb right here, we can just take 10 to the negative power of that. That gives us the Kb. This is going to then be x, once we solve for x, equals 3.11 times 10 to the negative 3. Could have we assumed that bottom x value? That would have been a difference of 3 here. So if it's multiple choice, sure. Okay. If this is not multiple choice and you have to come up with exactly a number that has 3 significant figures, no. Okay. That would have actually caused you to be a little bit off. You would have been something like a 0.097 or something like that. Okay. Now, if we go ahead and take Kw over this number here, we will get the H plus concentration. We can take the negative log of that, and that'll give us our pH, which is 11.49. Now, notice again, we started with a base, so our pH should be basic, right? Okay, So region B, this is going to be a buffer region, and at this case, we just have the Ka2, which is the fully protonated diprotic acid here. So we just need to use the Ka2. Okay. So, again, if we're at 1/2 of VE, then this would be 5 milliliters. The pH would equal the pKa, right? So if we take the pKa2, which is 14 minus 4 here, that would be 10. Okay? And so that right there would actually be the 50-50, where we're at the 1/2 VE. Okay, so let's look at the next region here. This is where we have to start actually doing things that we talked about when we were talking about diprotic acids, right? Because we're going to start having two Kas that are going to be close enough, they start interfering with each other. Okay? And so at VE1, all of your B has been converted into the BH+. And so when we were talking about diprotic acids, when we talked about BH2+, that was the acidic form, right? And then we had the BEH+, and that was going to be the intermediate form. And then we would have had the basic form, right? So notice we were working with the basic form before, weren't we? Okay. Now we're going to be in the intermediate form region, right? So we have to work with the intermediate form, which means we have to work in this K1, K2 environment, don't we? Okay. So the first thing we need to do is we need a formal concentration, because everything requires formal concentrations in these problems. Okay. And so what would our formal concentration be at this point? At the VE1. Well, we had 10 milliliters that we started with, right? And now we've added 10 milliliters, haven't we? And so our formal concentration 0.1 times 10 over 20. Okay. 10 plus 10 down here. Right? Okay. This is our new formal concentration at this point. We need to go ahead and add those into our calculation for the H plus concentration at the Ka1, K2 intermediate form region. And so we go ahead and put those numbers in. This is K1 here. This is the Ka2. Anybody know how to get these numbers right here? The 5, 10. 14 minus 4 is? 10. 10 to the negative 10. 14 minus 9 is? 5. 10 to the negative 5. Okay. That's our formal concentration right there after our dilution. We go ahead and plug these in. We do the math very carefully because it's very easy to mess up, right? By the way, do you actually have to do the math right there? If I subtract 100 minus 0.0001, doesn't matter. And so 10 to the negative 5, this doesn't matter. You can just put this value, right? Notice, though, that like your multiplications very much matter, okay? So you got to be really careful with multiplications. Okay, so we go ahead and solve all of that out. We get this value for H plus concentration. We take the negative log of that, and we get the pH. Anybody have any questions there? Not lose anybody? Okay, now, at D, if I go back up to D here, okay, notice it's down here, right? So this was that VE, right? This is the after the VE. So we've went past the VE now. We're at the region D. Okay? Okay. So at the point between the VE1 and VE2, the solution will again be a buffer that's going to contain the base BH plus and the acid BH2 2 plus. Okay? So you're going to have your 1-protonation intermediate form as your base, and then you're going to have your 2-protonation acidic form as your acid. We're in the next buffer region. Is that making sense for everybody? Okay. So your pH again, Henderson-Hasselbalch equation. Again, notice that the Ka for the BH2 plus is going to be the Kw divided by the Kb2, which is that second basic form. So we go ahead and plug that in here, plus the log of the concentration of the more basic form over the more acidic form. Okay? Everybody notice I'm being very careful in my language there of more basic, more acidic, rather than this is the absolute acidic form, right? That's the most acidic form. This right here, though, is the intermediate form. Okay? It's more basic than that acidic form, right? And so it is the base for this case. Okay. So at 15 milliliters, I'm going to go ahead and plug those in. And again, how far is that along my VE for this? What is my VE value for this buffer region? Is it 10? No, I'm past that, aren't I? Okay. So it's 2 times VE1. It's the VE2 region I'm going towards now. Okay. And so this value up here, this is going to be the 15 milliliters, or 1.5 times the VE. Okay. 1. And that means it is, out of 2, VE2, isn't it? Okay. Okay. So once I plug those values in here, I'm going to go ahead and solve. This is going to give me a pH equals pKa because I'm actually halfway through, aren't I? If I'm at 15 milliliters, well, minus 10 would give me 5, right? So I'm 5 out of 10, aren't I, for my next VE? So I'm exactly half. Okay. Okay. And so E, this is going to be at the VE2. And notice that at this point, we actually have our fully protonated form, don't we? And so this is actually just going to straight up be the equilibrium for the most acidic form of that diprotic acid. And so we just do the equilibrium for the acid now. That's all we have to deal with. Okay. This is your payoff for getting this far. You get a relatively simple equation again, right? Okay, back to normal acid-base reactions. Okay, so again, don't forget though that your Ka1 here, which is your most acidic form, your first deprotonation, this is going to be Kw divided by Kb2, right? So don't forget to get that value. Also, don't forget, we're going to be another modified formal concentration. So that's going to be the 0.1 molarity times 10, which is the original volume of your base, divided by your total volume of the solution, which in this case is going to be 10 plus 10 plus 10, which is 30. Okay? Okay, so you have your formal concentration, you plug that in, you have x squared minus x. This is going to be equal to your Ka2, which is 10 to the negative 5. Note that that's not a huge amount of difference from here. So again, if you're multiple choice, you could probably get a pretty decent answer and probably get it right. Okay, as long as the answers were far apart. But if you're not multiple choice or your answers are not far apart, you are definitely going to have to plug this in and do the quadratic. Okay. Take the negative log, you get pH equals 3.24. Okay. After VE2, what are we looking at? Yeah, we're just excess acid, right? So again, this is just going to be pure up dilution of your excess acid. That's all you have to worry about because we're using a strong acid to do the titration, right? And so, dilution factor right here times the concentration. Take negative log of that. That gives you your pH. Now, some titrations do not show both endpoints. So if we were to look at curve B here, see this gray one? We don't actually see both endpoints here. Okay. The BH plus is actually too weak a base to give a perceptible break at the VE2. And so when you do this, this would be like nicotine, by the way. So our PKB2 and our PKA2 are like very, very mild for this second part. So we would have a lot of difficulty actually finding that second endpoint here for this one. And so do note that you can sometimes get titrations where to the visual eye, it just looks like one titration, right? But do you see how this looks weird here? Like we don't get a nice buffer then leveling off, do we? See that? We get like another boom. And that's because that's the second VE right here. Okay. That's why we get the second log tweak. Yeah. Okay. So let's talk about a pH electrode. Now, in alkalinity, you have a quantity of base. It's going to be mostly carbonates and a little bit of hydroxide. It's going to react with strong acids with pH sample a little lower than 4.5. If we express it in millimoles, the pH of lower than 1, it's going to be pH 4.5 here for the alkalinity is approximately going to be the OH minus concentration, 2 CO3, 2 minus concentrations, and the bicarbonate, which is the HCO3 minus. Okay, that'd be typically what you'd find in like an oceanography estimate. For example, you could use this to see how much CO2 is coming from humans by calculating how much we currently have versus how much we historically would have had. Okay. Now, the alkalinity and hardness are going to be important for characteristics of, for example, irrigation water. The acidity in natural waters, the quantity of the carbonic acid and other dissolved acids reacting with the strong base, and the pH of the sample is raised to 8.3. Anybody notice that these 4.5 versus 8.3, they're not pH 7? Why would that not be pH 7? We have acids and bases in our system, right? And so you need to get it fairly acidic and fairly basic to really differentiate between these quantities, okay? Because again, it's a pretty complex buffer system. Now, if we express the millimoles of OH minus needed to raise the pH of 1 kilogram to pH 8.3, we would actually get the alkalinity and acidity of that system. This is actually what that pH versus the HCl looks like, in case you're wondering. So when you're monitoring pH during a titration, it can help in several different ways. So we can determine how much analyte is present. We can measure the equilibrium constants. This is what it actually looks like. Here's the pH right here, right, versus our volume of our base we're adding. Okay. That's very similar to what you all did in that first lab with the, second lab where we used the pH meters, right? Can everybody see that? It's just a little bit more careful. Okay. Everybody see your two equivalence points? Where do you find those equivalence points the easiest? You can either use the first derivative, in which case it's the peaks. The second derivative would actually be these 0 points right here, where it drops to 0. Okay. Now again, we can use these to compute our first and second derivatives. All you do in those cases, you just take the changes. Remember how I've shown you all the spreadsheet and how you can take the changes right there? And I did that with your data in the class. Okay, that's what I did here. I just did the first derivative because it's easier. I didn't have to do it the second because it's pretty obvious from the first. Okay. If you do the second derivative, it would just be the lowest value. You'd take the value closest to 0, not the lowest, but the value closest to 0. Okay. All right, so I'm going to skip that, but in case you guys didn't understand how to do it back in the lab when we did the analysis in the lecture, it's the same thing as that. Okay. Again, this is the grand plot right here that we did. So when collecting data manually, there may only be a few points near the end. You can use a grand plot instead to use the data from just before the VE instead of the VE, which oftentimes you miss because you didn't have a perfect indicator or you messed up, right? I'm sure that you all can relate. Because actually it's kind of a pain in the ass to get the VE, right? Yeah. It can be difficult. Okay. I don't blame you. I've missed the VE before. Everybody does. So again, your grand plot is going to be your volume of your base times 10 to the negative pH versus the VB. And you always use the 0.8 VE to 0.9 VE, that region just before your VE. Okay? And so notice again, this would be that 80% the way there, 90% the way there. In this case, it's closer to 90% the way there. And this would be your VE right here, which is going to be your last point. That's the final point there. That's going to be your intercept here. Okay? Notice you always want to use that region just before. Okay? This exact place that you're going to stop can actually be kind of difficult to do. See how it gets nonlinear when you get to the VE? Technically, you do not want to use the actual VE point. You actually want to use the point just before. Okay? It can be very difficult, though, and what you need to do is look at the linear response of your data and take out points until you get your linear response to your data. Okay? Okay. So this again, let's look at that titration of your weak acid. In this case right here, we actually have activities in here. So notice it is necessary to include activity coefficients because if you use pH electrodes, they're going to respond to the hydrogen ion activities, right? The numbers they give you are not actually the formal concentrations, are they? They're going to be activities, okay? That's why, for example, when we were using our pH electrodes and you all went, do we have to do the activity coefficient? I went, no. You got it. Electrode pHs are activities, right? Those concentrations are the activities. Now, the A minus concentration is going to be the moles of OH minus delivered divided by your total volume. Notice this is going to be VB times the formal concentration of B over VB plus the VA. Your HA concentration is going to be the volume of the A times the formal concentration of A minus the volume of B times the formal concentration of B, the base, divided by the volume of base plus the volume of acid. Notice that's just combining all the terms that you can do a concentration and then do the dilution all in one go. Okay. Now, if we combine all of that together, we're going to get this equilibrium expression right here. And so this will be your equilibrium expression. We can actually rearrange this if you want to this form right here. Notice, what does this look like now? Okay, so we have right here the VB times the concentration of H plus. Does this look like anything else? This term right here would be 10 to the negative pH, wouldn't it? Okay, VB times 10 to the negative pH, as in like the grand plot. Okay, and then over here we have the Ka, which is the slope, isn't it? Okay, and then this term right here, which is your other form. Okay. So if we were to simplify this a bit, we'd actually get your grand plot. See that? That's just your grand plot. And so that's why we plot VB times the 10 to the negative pH versus VB. Right here. The x-intercept is actually going to be VE, because that's where this goes to 0, isn't it? Okay. And so the slope is actually the Ka times the activity coefficient of the HA over the A minus. And that's where you got that slope. Okay, so let's talk about indicators a bit. Now, acid-base indicators, these are going to be a weak acid or base whose various protonated forms have different colors. That always has to be true because that's what makes them pH sensitive, is they are some form of a weak acid or weak base. Okay? It's also why you always want to be careful and don't add a bunch of, you don't add a milliliter of indicator, right? You add like a drop or two, okay? Because they are acids and bases. Now, a color will predominate the solution if the ratio of that species over the other color is 10 to 1. And so that's where you're going to be able to start seeing color changes, where you've got a ratio of 10 to 1 concentration. What does that mean for your eyes? They're not exactly the most accurate thing, right? But in most cases where we're doing titrations, they're close enough. It's good enough. Because when you're doing most titrations, you're looking at like multiple pH units changing with a single drop, right? And so that means if you have multiple pH units, that would be 100 to 1, wouldn't it? Okay. And so you can get a 10 to 1 ratio pretty fast when you're looking at pH, right? Okay, so this right here is actually thymol blue, in case you're wondering. This would be the pH that would change. You'd have a 1 to 10 ratio between yellow and red. And then we'd go 1.7 pH, and you're going to have a 1 to 1 ratio, and that's going to give you the orange color. Okay? And then when you get to 2.7, that's going to give you a 10 to 1 yellow to red. And so you start seeing a more yellow color. Okay? This right here is, again, thymol blue in all its different colors. This is where the thymol blue comes from, by the way, the base form. And so red, and see how it goes to the orange color right there around pH 2. And then you get to the yellow, and it starts going to like a greenish color around pH 8, right? And then you get to pH 9, it's more blue-green. And then after pH 9, it's blue. Okay? And this is what you're seeing. It's literally a titration curve you're seeing of the indicator, aren't you? It just happens to be colorful. Okay? And so remember the predominant species we had been talking about at different pHs? That is what an indicator's taking advantage of. You're just looking for places where it's 10-1 ratios. So this is phenolphthalein. It's an indicator that's used for its colorless to pink transitions at pH 8 to 9.6. Your transition range is actually the pH range over which the color changes, in case you're wondering. Okay. Thank you. Okay. This is kind of interesting. These are contributors that developed different methodologies. So if you ever want to know like who works in those fields lately, that's a kind of interesting place. If you're kind of interested in one of these topics, you can actually look up their names. Okay. Now, the acidity of a strongly acidic solvent is going to protonate the weak base. This is actually called the Hammett acidity function, which is 8,0. This is actually the Hammett acidity function. H0 equals pKa. That'll be the pKa for the BH plus form, plus the log of the B over the BH plus form. Notice that it's a derivative of the Henderson-Hasselbalch, essentially. Okay. For dilute aqueous solutions, your HO is going to approach the pH. When you have more concentrated acids, the HO is going to measure the acid strength instead. So the weaker the base, the stronger the acidity for the solvent must be to protonate the base. When we refer to negative pHs, we actually mean HO concentrations. The negative pHs wouldn't actually exist in our typical pH scales. We need concentrations that would be outside of their usual activities. So anyways, this right here is your mole fraction of your acid. And you see here, we get to the HOs here, and they get negative up here. Okay? Okay. We're going to start up on the next chapter next time. If you have any questions on this, let me know. One of the more important regions where it's a pure definitional region, it just requires memorization, is primary standards, okay? And so when you're looking at a primary standard, remember you're going to use that to calibrate something else. Okay? So it may not be the easiest to use, but what it is it's going to be pure enough, stable enough to be used directly after weighing. For example, NaOH is not. It would accrue moisture as it sits out, right? The entire mass can be considered a pure reagent. Again, that's a high purity. And the NaOH and KOH, definitely not good pure standards because they're going to contain carbonate, they're going to absorb water, they'll change as you try to measure them. Terrible standards. Okay? That's why they're never used. These are lists of primary standards that can be used as primary standards. Okay? And you'll use them to standardize a solution, which you guys have done quite a few times now, right? Okay, again, let me know if you don't understand anything in any of the material. Has everybody had leveling effect? Okay. You probably haven't had leveling effect. If you get a chance to talk. I think everybody else has, right? Leveling effect was what I was talking about. You can't have a stronger acid than water in water. That's what leveling effect is. So if you put a stronger acid than water in the solvent water, what will happen is it'll all react with water, right? And so if you put a stronger base than water in water, it's all going to react with the water, right? And so whatever your solvent is, it is the strongest possible acid and base in solution. Okay? And so, for example, strong acids are literally acids that are stronger than H3O plus. And what happens is they just form H3O plus in solution. Okay? Strong bases are just bases that are stronger than OH minus. And so in water, they just form OH minus, right? If you change your solvents, you can actually get different solvent regions. And so you can get stronger bases, stronger acids than you normally would be able to. Okay. Organic is pretty infamous for it, where things like that would normally be a base in water can actually act as acids. Because the organic compounds let you go way up there for your Kas. So you can go at pKas of like 55 and be acidic and have things that are basic at those. Okay. Okay. All right. So let's go ahead and we'll call that a day. If you guys have any specific questions, let me know next time, and I'll hit those topics out in more detail. Okay. Anybody have questions? Tap